Alright, time for Volumes of Revolution Part 2, using the washer method. This time, the regions we get after revolving around an axis will have a hole in the middle. And when we take our slices of these regions, we end up with an object that looks like a washer. Thus the name the washer method. Now I've got a picture of a washer here. To show you how to find the volume of it, let's do this. I'm going to draw on it. There's the center to the outer edge, and then you have another radius from the center to the edge of the hole. Well, let's assume that the outer radius is, let's say, 30 millimeters, and that the inner radius is 10 millimeters. And let's say that the height of that washer is real thin. It's about 2 millimeters. So if we were trying to find the volume of that washer, again, the volume of a cylinder, pi r squared h. Now first, let's just assume that there is no hole, that it was solid instead of having that hole in the center. Well, the volume would be pi, the radius is 30 squared, and the height is 2. And there's the volume, and we could work that out. But since the hole is in the center, that's going to take some volume away. So what we would do is subtract the volume of the hole. So the volume of the hole is pi times the radius of the hole, which is 10 squared, times the height, which is 2. So overall, we have 900 times 2, which is 1800 pi for the entire washer, discounting the hole, and then subtract out the volume of the hole, which is 100 times 2, or 200 pi, and we're left with 1600 pi. So the volume of the washer is 1600 pi cubic millimeters. Now we're going to do something very similar in using this technique called the washer method. So let's go to an example. Here's our first example. Find the volume when the region bounded by y equals x squared, which you're familiar with, y equals 4, x equals 0 is revolved around the line y equals -1. Okay, let's take a look at that graph. I had the solid in the picture, which I took out. We'll get back to that in just a second. So the region that we're talking about that's bounded is, again, the yellow region. It's trapped by y equals x squared, the red curve, the line y equals 4 across the top, the y-axis. So we had that region in the first quadrant. Now we're going to take that region, and this time we're going to revolve it not around the y-axis, but around the line x equals -1. So let me do that for you so you can see what this region looks like after we revolve it. Alright, here comes the volume. Starts, goes around back, and comes around front. Now it's going to be a similar looking shape to ones we had seen before. It's kind of that bowl shape. However, the difference this time, if I tilt this, you'll be able to see the difference is it has a hole in it. And that hole goes all the way through. So in order to find this volume, we're going to use integration just like before. We're going to slice it up into very thin cylinders just like before, but we're going to have to subtract out the volume of the hole. So we're going to need to know two different radii. So what I'm going to do that, let me take this picture and copy it. And we'll go back to the drawing board and work that out. Let me create some space here. Alright, there's our picture. Alright, just like in the previous lesson, the first thing you want to do is slice the shape perpendicular to the axis of revolution. So there's our slice. And I want to change colors on this a little bit because it's kind of hard to see, and I'm going to color it in. So there's our red slice. Now that red slice is actually except it went away. Come back. There it is actually a washer. So let me take that off of there and give a crude rendition of what it looks like. There it is, very crude. But anyway, you get the idea that it's a thin washer, just like the first picture I showed you. And what we need to do is to find the two radii. So to find the volume of a washer, you find the volume of the whole complete washer, and then you subtract out the volume of the hole. Or sometimes I'll say use the outer radius and then subtract the inner radius. Alright, so let's find the outer radius first. The outer radius is the distance from the axis of revolution. Now that axis of revolution is located at x equals -1. So the distance from there to the outer edge of the original region. So there's the radius. And on my side picture it corresponds to that. So how long is that? Well, let's set up our integral. And since the thickness of that cylinder, a very thin cylinder, is going vertically this time, up and down, we know that that is dy. So everything has to be in terms of y. All right, back to finding the length of the radius. Well, the right-hand side is the curve, which was y equals x squared. But we need that in terms of y. And remember, we did that in the last problem. It's x equals the square root of y. And the other red dot on the left is x equals -1. So to find that length, here comes the tricky part. To find that length that I have marked, it's going to be the right point minus the left point. The right point minus the left point. It's just like finding the length of this segment. If I said, okay, that's located on the number line at 0.5. And this endpoint is at the number 1. How long is that line segment? Well, obviously it's 5 minus 1, which is 4. So you always take the right end minus the left end. Well, the same thing applies to this radius. The right end is the square root of y. The left end is -1. So we take the right end, the square root of y, subtract the left end of -1. This is the representation of the radius. So let me come over here and just put that in my integral. The square root of y subtract -1, which is the same as +1. That's the radius. And what do? We square that. Remember, it's pi kicked out front, radius squared times the height, which is dy. And since everything is in terms of y, the limits on the integral are from the bottom y point to the top y point. Well, the bottom y point is 0, and the top y point is 4. So let me highlight this. What we just set up will give us the volume of the whole complete shape. But we know that's not what we want, because that's more than what we want. We have a hole in the center, which we have to subtract out. So now I'm going to subtract out the hole. Well, once you got the outer one figured out, the whole tends to be a little easier because the limits of integration are the same, 0 to 4. Pi is still out front. We know it's dy. And the radius of the hole, let me erase some of this on here, and we'll go back to the diagram. Now the hole is about in here. Let me sketch this in. There's the hole that runs right through the center of this shape. All right, so we have to find the radius of the hole. Well, the radius of the hole is, again, the right point minus the left point. Well, the right point, if you remember the original shape, let me see if I can highlight this in a dark color so you can see it. The original shape is in here before we revolved it around the line x equals -1. So the right point of the hole is where the side of the original shape was, and that was located at x equals 0. So the rightmost point is 0. The left point of the radius is on the line which we revolved it around, which was x equals -1. So the radius is the right 0 subtract the left -1, which is equal to 1. Now if you think about it, that makes sense. How long is that radius? Well, it's just the distance from there to there, from the axis of revolution to the y-axis, which is 1 unit. So the radius squared is 1 squared. So the second integral, which I just set up, which I'm highlighting right now, represents the volume of the HOLE, hole. So to find the total volume of the region, we would take the two yellow highlighted integrals, calculate them, and have the answer. I'm not so worried about the integrals and the calculation of those. I'm sure you've got that down. So the important thing about this video is we learn how to set these up. So on this problem, we're going to stop right there and move on to the next problem. And if you want to go ahead and calculate that, you may freely do so. Okay, we're going to have one more example of using the washer method, similar to a problem we've done before. I changed it just a little bit, but you'll see on this one, we're going to slice it in the other direction. Now, if you understand these two problems on this video, then you should be able to do any washer problem. Because once you get that technique down, they're virtually all the same. It uses the same technique. Of course, they may be different equations. They may be revolved around different lines other than x equals 1 or y equals -1 or whatever. But the technique is what is the important thing here. So here is the problem. Let's go to the graph. Okay, so we've got the red graph, which is the square root of x plus 2. And it's bounded by the y-axis on the left, and it's bounded by the x-axis on the bottom. So the area is the pinkish region. And we're going to take that region and we're going to revolve it around the green line. Now the green line is y equals -2. So let me do the revolution here. All right, here goes. Again, pretty much the same basic shape, kind of the bowl shape, but this time it's turned on its side. And let's take a look. Where is that hole? Oh, there it is, running right down the middle. Let's look all the way through it. All right. Okay, let me revolve this back. See how you can kind of see the individual lines where it looks like a stack of washers, just stacked up different size washers to form that shape. That's the name, the washer method. Okay, let me copy this again. I'll copy the page and we'll take it back to our work page and calculate the volume. Let me scroll this down, paste it in. Here we go. Okay, general form. The volume of the WHOLE subtract the volume of the HOLE. Okay, now this time the cylinders are going this direction, up and down. So the width or the height of that cylinder is just this little distance going horizontally, which is represented by dx. So let me set up my integral. I'll put one integral there for the WHOLE minus the integral for the HOLE. Let me stick a dx on the end of each one. I know I've got a pi out front. Pi out front. The only thing that's left, the radius. Alright, so let me draw in the radius for the hole, which goes, let me kind of put it here so you can see it. From there to there. There's the radius. Now, remember the radius starts at the axis of revolution, so I've kind of lined it up with that green line, which is the axis of revolution. Okay, so that radius, what's it hitting on the top? Well, it's hitting the curve. The curve is y equals the square root of x plus 2. So we're trying to find the length of that radius. What's it hitting on the bottom? It's hitting the line y equals -2. So the length of that radius is the top endpoint minus the bottom endpoint. Or in other words, I'll come back over the integral to write it. The top endpoint, the square root of x plus 2, subtract the bottom endpoint, -2. Alright, what I just wrote and put in parentheses there represents the radius of the whole WHOLE thing. And let me not forget to square it. Alright, now we need the volume of the HOLE. So, where is the radius? Well, the radius goes, again, from the axis of revolution to the edge of the hole. Now see, I know the edge of the hole is right on the axis because the original region was above the axis and below the curve. So now, what's that radius? Well, again, common sense would tell you how long that is because it's from 0 to -2, which is 2 units. But let's look at it this way. That top point is 0. The bottom point is where the axis is, which is -2. So it's top 0 subtract bottom -2, which equals 2. So as we said, we knew the radius was 2 squared. Now here is the complete setup to find the volume of that lovely shape. And again, this integration is a little tricky. We did one similar to it. Now you could clean up this first integral. We have +2 minus a -2. So let me clean this up a little bit. We might not go ahead and finish it, but inside the parentheses, the square root of x plus 2 minus a -2, which is the same as +4 squared dx. The second one, the HOLE 2 squared is 4 dx. Now we also need the limits of integration. Of course, we're dealing with x here, so we go from the left endpoint of x to the right endpoint of x. That's a little deceiving the way this picture's turned, but if we go back to the original graph for just a second, let me turn this back so you don't get tricked. There we go. You can see that the left endpoint of this region, the x point on the left end is 0, and the right endpoint is 4, because the original interval was from 0 to 4. Let me take this out. I'll take that volume out so you can see it again. It's a little easier to see there. 0 to 4, and put it back in. There we go. So there's the volume. And there it is without the volume, without the revolve volume in there. Alright, so let's go back and finish this. So all I have to do is put in my limits of integration. 0 to 4, 0 to 4, and from there you would just perform the integration and you would have the final answer. But as I said earlier, the important part right now is just being able to set it up. Alright, so we're going to stop there with volumes of revolution using the washer method.